So last class we discussed about the first interface for a microprocessor unit with its outside world, and it was on GPIO, and we understood what is a GPIO, how it helps in interfacing with the outside world. Even though it is quite trivial, it is one bit at a time. You can combine several such GPIOs to act like 8 bits at a time, for example. And the beauty about GPIO is like you can configure it as an input or as an output. So we discussed about all those aspects. And now in this lecture, we are going to discuss about a very, very powerful concept, a very interesting concept in microprocessor systems, which is interrupts. We casually discussed about interrupt quite a few times in the last few classes, in this course at least, many times. So there is a reason why interrupts are there and interrupts are so popular. So as the name suggests, as the meaning of the word itself suggests, it is an interrupt. Okay. So this is an external or an internal device request. The microprocessor may be connected to so many peripheral devices. Those devices wants to communicate to the microprocessor, then it wants to interrupt the microprocessor. It will issue a command so that microprocessor stops, listens to them, and does something for them. I mean, in terms of how does it work out? Okay. So we'll go into these details. So we'll not explain all these things at one go. Let's actually see in a more pictorial way how it represents. So the depth axis in this case is the time. So typically a program will be running over time, and this is the main program, the blue shaded one. So this will be a chunk which will be executed one line at a time sequentially. Are sequential programming devices. So one line executed, next line executed, and so on. And suddenly at this point of time, the microprocessor receives an interrupt. Okay. So what happens during that time is it stops executing the main program. It does some hardware operations, some activities. We will discuss about that in very detail, what is exactly happening here. And then it starts and execute a certain routine. We call that as interrupt service routine, or ISR. Okay, so you can write whatever you want inside this routine. Suppose, let's give an example. I want to press a button, and when I press that button, I want to blink an LED or toggle the color of an LED, for example. So when I press the button, it triggers an interrupt to the microprocessor. And then microprocessor, as we can see over here, and does some operation and goes to a routine. And inside this routine, I have to write a code to blink the LED. And once that part is done, it just restores what it has done already previously, or sort of basically nullify whatever it has done previously, and then comes back to the main program and executes the remaining part of it. So that is the concept. So main program is the thing that it is always executing, but in between it may get an interrupt. It goes to something else, some other function. You can think this as some other function, or in terms of assembly language, subroutine, executes what is inside this subroutine, and then comes back and executes the remaining, wherever it stopped, the remaining part of the program. So that is the concept of interrupt. In a more intuitive way, this best analogy somebody can give for a concept of polling versus interrupt is something like the alarm. Suppose I don't have an alarm. I want to wake up at 6 o'clock. What we typically does is we may get awake at some point of time, immediately sees the clock. The time is not 6 o'clock. I continue sleeping. But again, I won't get a fluent sleep, right? I will be between and poll the clock and see the time and see whether it is 6 o'clock or not. And if it is 6 o'clock, obviously I will wake up. But then there is a chance that I may miss 6 o'clock. That's a problem. So that is polling. On the other hand, interrupt, you put the alarm, and at 6 o'clock sharp, it triggers the alarm and you are awake. So that's the concept. So when I was a child, this telephonic system was old landline connection. And STD, ISD and all is sort of a luxury. So then if you want to call an STD or an ISD, you have to call the telephone booth, book an appointment, and then they will call you back with the number that you give, the ISD or the STD number that you give. So what you need to actually do is then wait for that call. That is something known as polling. So now you don't need to do that, right? So it's a very, very difficult, tedious task to do. Let me put some context into the picture. Last lecture, we discussed about GPIOs, right? And we discussed about how a GPIO can act as an input to a photodiode. So think about polling. In the case of polling, that GPIO pin has to be, or that GPIO register has to be read at a certain interval of time to see whether that is updated with the value in the photodiode. That's a very tedious task, right? Instead of that, whenever the photodiode becomes active, if you trigger an interrupt, you can make GPIO as an interrupt triggered one, then that's much better than just polling, right? So that's the importance or power of polling versus interrupts, or the power of interrupt rather. Okay, so moving on, there are many types of interrupts possible, of course, in microprocessor system. You can see over here, there are some which are actually based on software alone. One classic example is something like you try to access an area in the memory which is not accessible. Immediately triggers, only many times back, it triggers a best fault. It's known as a hard fault. So that definitely triggers an interrupt. There is a software interrupt. And what happens during that? It goes to a hard fault routine. There is some interrupt service routine dedicated to that. And typically it is blank. You can fill in something there and it works. Okay, and then comes back to the execution of the program. Something like you can display error. You're trying to access a non-accessible region. So please don't do that. That's what you can write inside the service routine of a hard fault interrupt. On the other hand, hardware, there are two types typically, non-maskable and maskable. So non-maskable means they are really high priority interrupts and you cannot do anything to mask them. They will be always running. So something like probably maybe nowadays even temperature rise in a system is non-maskable because it goes beyond a certain limit. You just need to restart. There is nothing that you can do. So they are non-maskable. CPU cannot mask them. They will be always there. But then there are maskable interrupts where CPU can mask them. So even if it happens, just be ignorant to it. But they are also important. But most of the time, there is a provision to mask them. Okay, they can come from external sources and internal sources. Now let me show you some examples. Software, as I said, divide by zero. Answer is infinity, and there is nothing like infinity in a computer system, right? So it overflows the stack. And it's not the stackoverflow.com. Okay, we might have inspired from here, but yeah, this is something known as stack overflow, and it is actually an exception or a trap, and it is actually a software interrupt. Non-maskable, a classic exception is memory corruption. If you really make a mess of your memory, sometimes like heap and stack getting overlapped and all those things, it is a non-maskable thing because your memory is corrupted. You cannot do anything. You just need to restart the system. So it is non-maskable. And internal sources increase in temperature. Nowadays, it is actually put under non-maskable, but traditionally classified under maskable internal sources. And external sources are plenty of them. Any interface that you can think of, including the GPIO, can act as an external interrupt, and they are maskable. Okay. And just a note here: the software interrupt, typically they don't call as interrupts, software interrupts. They call it as traps and exceptions. Moving on. Another way to actually represent the whole concept I was telling, if there are no interrupts, a CPU will continue to execute a sequential main programming without any interruption at all. It just does that. Then you have so many peripheral devices, so many other aspects which is in and around the CPU. You want to communicate to CPU, polling is one option, which is a very, very trivial, tedious option. Instead of that, it's better to actually something like interrupt. So GPIO, when something is there, it can actually. Now there is a problem. I have so many peripheral devices, all of them starts to interrupt the microprocessor. What to do? That is where modern day microprocessors have something which is controller which can actually prioritize these interrupts. Of course, some of these prioritization is done by you as a programmer, and based on the priority, suppose GPIO interrupt is higher priority than ADC interrupt, then it will be given first preference, and that interrupt service routine or that function will be executed before the lower priority interrupt. Okay, so that's the concept. So as I said, if you have any questions or doubts, please feel free to raise in the respective discussion forum. We can always discuss them. Moving forward, this is a very lovely picture that I draw for you, and it's sort of a very, very holistic view of a microprocessor. And highlight all the previous classes except the last lecture, we were all seeing inside. We never saw it outside. Now this is a world for us. So this is something like a chip you can think of, an entire chip here. You have the pins or the mapping out of your entire system on chip, and so on. This is just an illustrative representation. It is not anything that realistically there, but something similar will be there. And then, as I said, one pin can act as multiple options. So in this case, for example, the same pin can act as GPIO as well as UART. So what is that you will do? You have to do that pin multiplexing, the signal multiplexing register. You have to configure it so that it will act as GPIO or act as UART. Always remember that. Okay, the same concept here. Okay? Similarly, this pin, I'm just illustrating it. It is multiplexed between SPI, which is a serial peripheral interface, a serial protocol, and I2C, which is another serial protocol. So you choose whichever you want. And similarly, I'm just giving a very crude illustration here of ADC may be directly mapped to the input output. And all these peripheral devices, basically these are the individual configurable controllers. GPIO controller, we discussed about all the set of registers, the output registers, the direction register, the input register, all those. Similarly, other peripherals also have their own registers associated with that, right? Those registers, again, something like a memory location, memory mapping for the microprocessor, they are connected through the bus to the core, right? So that bus is our friend all the time. And similarly, there's a memory unit, the SRAM unit, or even the flash memory unit, which is actually connected to the core through the bus. So inside the core, what is there? Inside the core, it's only registers and I/O, right? And maybe some other logic circuit. That's all. And then this part is what we should focus in this lecture, which is actually something which is a friend for you, network vectored interrupt controller, NVIC. That's what the short form is. This guy is what helps us to prioritize the interrupts and ask or tell the CPU to execute this one first, this one second, and so on. So this is something, a digital circuit, of course. This is a logical circuit here, which actually has so many registers and so many control circuit inside, which takes the input from the bus, which are basically the interrupt requirements, and then prioritize it and give the output to the CPU so that you are actually relieved from all these trivial tasks. And it works on the basis of an interrupt vector table. That's a prioritization table, which is actually having the address of the subroutines for each of the interrupt service routines. So for example, GPIO has an interrupt service routine. That address will be stored in here. UART has an interrupt service routine. That address will be stored here. But then all these locations will be stored in some prioritization order. That we will discuss in the next few slides. And then what is this black? Black is the typical polling based architecture where you actually connected to the bus and connected to the CPU through that, or core through that. The red line is the interrupt option. So you can actually configure the GPI as an interrupt, then it won't communicate through the polling route, it will communicate through the interrupt route. And all these interrupt things will get concatenated and comes to the NVIC, the nested vectored interrupt control. And then this will decide the priority of execution of these interrupt requests. So that's a concept. So don't worry about it, even if you didn't understand this concept, we will revisit it many, many times. But the underlying principle is that there is a conventional polling route where everything is through bus again, but it is actually individually connected through the bus to the core. But there is a interrupt routine also, which is connected through the NVIC to the core. So that's a basic difference. But in both cases, bus is our friend. Bus is what actually connects each individual component to the corresponding core. And of course, don't always forget this guy, which helps us in multiplexing these options to the pin so that we can interface with outside world accordingly. So this is a very, very crude representation. I encourage you to go through the manuals and see very detailed explanation of how each and every part of the circuit works. Okay. An interesting part is that more or less any microprocessor unit that you take will follow similar principles. Moving on, so now let's concentrate on this guy, NVIC, and explain in some detail how it looks like. So it is definitely an array of registers, but there are definitely some logic circuits so that it does what it does, right? So just to give an idea, NVIC supports somewhere around 32 interrupts for our case. For Cortex M0 Plus, it supports around 32 interrupts, all the way from 0 to 31. So 32 interrupt options configurable by you are available. So that's impressive, right? 32 sort of interrupts. Now, out of these 32 interrupts, suppose all of them comes together. All the interrupts comes together. Then you need to have a priority. So typically, a Cortex M0 Plus has this flexibility of priority. It can go from level 0 to level 192 in steps of 64. That means lowest level is 0, next lowest is 64, then 128 to 380, sorry, 250, 256, correct? Yeah, okay. So and so on. And the most important thing is this one. 0 level is the highest programmable priority. That means if some interrupt is having level 0, that is obviously the highest priority. Okay. And situations can come that 2 interrupts has the same priority level. Then of course, first come first serve is the only solution. Okay. And the important part actually is just to confuse you. Sorry for that. This is the information provided by Cortex M0 Plus, but for our Freedom board, it has a slightly different approach, which is actually shown here. Okay. So this is what Freedom board follows. So it has only what you call 4 levels of priority because 2 bits at a time. So 0, 0, 0, 1, 1, 0, 1, 1. That means 0, 1, 2, 3 are the levels. 0 of course means the highest priority and 3 of course means the lowest priority. And this entire set is for one interrupt. Okay, so let's say the 0th interrupt or the 0th interrupt, will have, let's say I put 0, 0 here, which means the highest priority. And so on. We'll come to this in some detail as we proceed. Okay. And then if you see inside the NVIC, what is inside? There is a lot of logic circuit. In addition to that, it has 5 registers built into it. And see the location. So always go back to that memory map we have. And this is somewhere at the top of the memory map. Okay, towards the end because address location is somewhere around 0xe. Okay. So these are the locations at 0xe000e100. We have a register named interrupt set enabled register. What is inside this register? It has 32 bits. That means 32 interrupts or 32 locations, 0 to 31. So if you make 0 to 31, so default it will be, you can actually go back and see. So let me actually quickly show where you can find this register. I'm sorry for that. You always go back and see these 2 documents. Okay. So basically this document as well as this document. Okay, both I will upload to the Moodle. This one you already have it actually. So these are reference actually. So if you see here, you can actually go through each one of them individually. If you go to the peripherals part, and then if you click here, you find whatever information I was presenting on the slide, and you can actually go and see individually what each of these registers mean. For example, the set enable register, you have to actually set this to make this interrupt enable, otherwise it will not work. So if you, let's say you connected some interrupt, but you have to enable this register, otherwise that particular interrupt will not work. Let's say, so 0 means no effect, that is by default. 1 means that you're enabling that particular interrupt. So here you have 0 to 31 bits, that means 0 to 31 interrupts. So if I make 0 as 1, the lowest significant bit as 1, whatever is connected to that 0th interrupt is enabled. That is the meaning of it. Similarly, the other register is clear enable register, and this you can actually do it to clear whether you have enabled that registers. Okay. Similarly, there is set pending register. So this you don't have to worry, NVIC will do for you. So only thing you have to worry about is this guy, set enable register, and then this last guy, the interrupt priority register. Okay. So you have to set the priority correctly. So that is what you should do here. So enable the interrupt using this particular register and set the priority of that interrupt using this particular register. And remember here it has how many? 0 to 7, 8 registers. So I'll just go to that location. So this is the case. So interrupt priority level for the interrupt 0. That's what here. It shows you 7 bits, but as I said, Freedom board doesn't take all the 7 bits, it only takes the most significant 2 bits out of these 8 bits. Sorry, not 7 bits, 8 bits, 0 to 7, right? 8 bits. Only these 2 bits are enabled. Similarly, 8 to 15, only 15 and 14 are there for Freedom board. But for Cortex M0, you can actually set some value 0, 0, 7, 8 bits are there. You can actually generally go all the way up to 192. That's what actually they're saying. Okay. But the problem for Freedom board is you can only set this. Now, just to give a feel of it, I'm not going to complicate things for you. This is the bit space to set the priority for the interrupt 0. Similarly, interrupt 1 here, 2 here, 3 here, and that completes 1 register altogether because 8 into 4 locations, right? So it's 32 bit already. Then another register is there, and similarly the last register NVIC IPR7, and this has the priority specification thing. You can do it for the interrupt 28, 29, 30, and 31. Okay, now let's go to this document. Okay, this document also has similarly all the things you can actually see over here, and you just go to the chip configuration and go down here. There is nested vector, this one here, and you can actually see the diagram that I was drawing for you. It's something similar here. And then you go here. This is the priority level I'm talking about. So this is not applicable for us. For us, if the board that we are going to work on, that is also we have to see the manual of that board. So that doesn't give you freedom to specify all the 7 bits. Rather, it will give you freedom to specify only these 2 bits, these 2 bits, these 2 bits. Basically, in all these, only the 7th and 6th, 15th and 14th, 23rd and 22nd, 31st and 30th. That's what you're going to show here. So it's a bit complicated, and I just want to show you an example. Okay. Or maybe before going there, what are these IRQs meaning? You may be thinking. Okay. So let me just go back here actually. So it's already there, and we'll come back. Okay. So we'll come back to this a bit in a moment. And as I said, if I go back here, the NVIC is a bunch of registers that we already discussed. There is something known as vector table, which is predefined for you. And that is where the order, the priority of the interrupts, the importance of interrupts is already predefined for you. So let's see that list. So this is a table that you're going to base upon. And if you see, these are the interrupts which are not in your hand. This is system defined interrupts, including some of the software interrupts like hard fault, for example. And these are reserved, you don't have any control for. So for example, I just want to make it very clear to you. These are the addresses of the memory map. So this is a very first address. Always remember that 00, all zeros, right? And that address has the pointer to the stack memory. Okay, so that has the starting address of the stack pointer. So that's interesting. When you reset, everything gets reset, and the stack pointer will come to the first location of the stack, and that value will be lying here all the time whenever you reset the system. The next, of course, 0 to 4, because this is 32 bit. So and each location is 8 bit. So each location is 8 bits, so you need 4 locations. That is why the address points to 4 here. And then here you have the program counter location. That is what it is actually typically when you see the Keel microvision, you will see what here. If you remember, some of you remember that. If you see, you will see a reset vector here. Okay, so that reset vector or reset handler address will be here. So it will go and execute that particular address or coding that particular address, and that's it. So when you switch on the system, this is where it comes to. It will initialize with the stack pointer, then it goes to this location where it initializes the program counter. The program counter will get the reset handler address, and then whatever you write in that reset handler will be executed. That's how we were doing so far, even though we didn't spend any time in understanding that. I will definitely explain that at the end of this lecture. Okay, again. Okay, so that is done. And then other things. So at this location, you have a non-maskable interrupt. Okay, so there is a provision for that, but we don't have any control on it. And this interrupt we will be playing with in the lab. So this is a hard fault. You try to access a non-accessible location. It immediately goes and executes something which is actually in this particular location, or whatever value that is addressed to a point, it's a pointer to a location, to an interrupt service routine, and it will go and execute whatever you write. So in assembly language or in C language terms, we call this as handlers. So here there will be the address or the pointer to something known as hard fault handler, and hard fault handler is nothing but the interrupt service routine associated with the hard fault. These locations are reserved for you. Sorry for it. I will just put the pointer option back. So these things are reserved for you. You don't have any control. This is something again reserved. You don't have control. So you can ignore all these. Nothing you can do about it. This also you can ignore. And this is something which is SysTick timer, which is something like a timer you can set. And the moment that time comes or that counter goes to that predefined value, it comes and executes. It triggers an interrupt, of course, and it goes and executes something which is there in the interrupt service routine, was address. The address to that interrupt service routine, which is associated with the timer interrupt, will be specified here. And all these, so you have around 16 of them. All these are actually predefined interrupts, and you can have no control on them. This is system defined interrupts. Okay, no control on them. And then beyond this, you have so many of them. This is what I was telling about 0 to 31. This is what which is actually controlled by your friend NVIC or NVIC or nested vectored interrupt controller. So these are all system interrupts. You don't have any control. Beyond that, you have 32 possible interrupts, and those are configured by you, and you just always have to come back to this chart. This is the table that is your friend. Okay, you safely can ignore this vector. This is actually in the increasing order, so 16 of them is here, and then it starts, so it starts from 0, so 0 to 15 is here, 16 of them of course, and then it comes from 16 all the way to 37, so 32 of them of course. And then this is the number, the interrupt number. Of course, if you go back and see the set and interrupt register, the zeroth interrupt, the 0th bit corresponds to DMA channel 0. So DMA is a direct memory access. If we have time, we will definitely discuss about it. But generally, I tend to ignore it because it is an advanced concept, which is something like a direct memory access or direct memory connection between the memory unit and the microprocessor. We will try to discuss it, but not in very detail, but we can ignore it. But this will act as an interrupt. It can act as an interrupt, and that is connected to the bit 0 or the pin 0. And similarly, 1 is another DMA channel, 2 is another DMA channel, and so on. And maybe we will go to something which we already know, which is way below at the bottom, which is port A and port D, which are the GPIO ports A and port D. And they are actually interrupts 30 and 31 in our Cortex M0 Plus as well as the Freedom board. Okay, so interrupt number 30 in our thing is actually interrupt coming from port A. and interrupt number 47 is coming from port D. So you can always go back and see which pin in port A. Port A itself has 32 pins, right? So which pin is actually connected as an interrupt. And that interrupt is actually the pin number 30, or the interrupt number 30 in the interrupt in the interrupt vector controller. Okay. And if you go back and see the Arduino board now, some pins are specified as interrupt, and the similar concept is applied there. And you are really fooled, or you are really made lazy by the processing software, because it's so easy to do. But you should always know it. As an engineer, you should know at this level how it works, right? So just to reiterate, this is a table which actually has the list of all interrupts possible. Some of them are system defined, some of them are flexible, and you can actually do a lot of things with this. And then 3 things you have to be remembering. There is a vector number, which is a sequential number for the interrupt. IRQ, which is actually only available for the interrupt which are controllable in the sequential order. And then this guy, NVIC IPR register number. Just have a look at it. So 1, 2, 3, 4. 4 of them are 0. Now, please allow me to go back to this guy, or maybe to this register. Or so this is what I was telling you. So 0, 1, 2, 3. So all these are zeros. NVIC IPR 0, right? Those are actually these 4 registers. So this NVR IPC 0, so they occupy that. So in the correct order, so 0 corresponds to basically this guy, and then this guy, then this guy, and this guy. Okay. Similarly, the 31 to 0, so those are here. NVIC IPR 7. So this 7 is what actually we are seeing over here. So NVIC IPR 0, these 4 of them, 1, these 4 of them, 2, these 4 of them, and 7, these 4 of them. Okay. Now I want to actually help you out a bit, and maybe some of you get complicated. I just wanted to, okay, this is entire list, whatever I copied into the PowerPoint. Let's actually, suppose you need to configure the SPI0 input. Following table is expert from here. SPI0 is here. Okay, this guy. Here is a serial interface, serial peripheral interface. They copied pasted for you the same table, only that thing. The address for the subroutine corresponding to SPI0 will be in here, and it is vector 26, IRQ number 10, NVIC IPR 2. Okay, so obviously you have to go and fill in the register NVIC IPR 2. So let's go sequentially. The first step you have to do is to enable this interrupt. How will I enable the interrupt? For that, you just need to go back to this particular register, the set enable register. And what is the pin number? Pin number for SPI0. SPI0 is IRQ 10. So that means bit 10 should be made 1. Bit 10 in this particular register, set enable register, should be made 1. And moment you make that, you are enabling SPI0 as an interrupt, or you are enabling an interrupt capability for SPI0. So moment you do that, you come back to this. Now I need to give a priority to the SPI0 interrupt. And that is what you have to look at, this number 2, NVIC IPR. So you go back and then put in this register, right? And so NVIC IPR register, which will be having a format which is something similar to this. Go to that register, and which one shall I fill? This one, this one, this one, or this one? That one is given by a very simple formula, which is actually listed here. 8 into IRQ number, which is this number, mod 4 plus 6. If I put the IRQ number, which is 10, into this, I will end up in having 22. That means 23rd and 22 bits of your NVIC IPR2 register should be set accordingly. So I can give 00, 01, 10, 11, any of these. And of course, 00 is the highest priority, 11 is the lowest.